If we have a graph of pressure versus volume, and we have, let's say we just have a point on the graph. If we just have a point on the graph, what information does that tell us?
It tells us, well, the point is a state function, and we can tell what is the pressure involved.
Yeah, pressure. Sorry, go ahead.
Oh, I said we can tell the pressure and volume at that particular state function.
Yeah, pressure, or I would say that the point is a state, and pressure and volume are state functions of that state, in the sense that at that point, there's a certain pressure and a certain volume. So pressure and volume are functions of the state we're in right now. So we've got, let's say we can call this an initial pressure and an initial volume. In fact, let's throw in some numbers there. Let's say that's, let's say 500 pascals of pressure. And let's say the volume is 2 cubic meters. And let's say this then changes to a different pressure and volume. We've got a gas in a container that's this much pressure, this much volume. And then let's say sometime later, it's a different pressure and volume. So let's say we've got a new pressure and a new volume. And let's say those values are, let's say it jumps up to 8 cubic meters and drops to only 100 pascals of pressure. And the process linking these, actually without even knowing what the process is, without even knowing what path, if all we know is the initial and final values, what other information can we figure out just from the initial and final values? Even if we don't know the transition. Work is actually going to require a little more information, but yeah, we can find the change in temperature. Because the thing is, on a graph like this, what tells you, or how would you figure out how much work was done on a graph like this?
You would need the processes, so the part that connects our two state functions together.
Yeah, if all you know is the initial and final values, you don't really know what process took you from initial to final. In fact, on a PV graph, if we did have the process, like if we know the path taken here, let's say we do know that the process is, let's say, a straight line. How would we figure out the amount of work done during that process? In general, how does work show up on a graph like this, a pressure volume graph? Yeah, work is area under the curve. And yeah, for sign, we've got to be careful. Specifically, in this case, it looks like the volume is expanding. If the volume is expanding, would you say work is entering or leaving the gas? Right. If volume increases, then work is leaving the gas. So we describe that as negative amount of work. Or if the volume is shrinking, if the volume is decreasing, then work is entering the gas because you have to do work to squeeze the gas into a smaller space. And we describe that as positive work. Generally, the sign of work being positive or negative value, is about, is the work acting to increase or decrease the energy of the gas? So work entering the gas is treated as a positive value. Work leaving the gas is treated as a negative value. And the same is true for heat. Heat being added to the gas is positive amount of heat. Heat being removed from the gas is a negative amount of heat. And yeah, generally the work done is the area under the curve, if you're talking about a pressure volume graph like this. So that would be the area from the curve all the way down to the axis. So this area, you measure that much area using geometry, or if you have the function itself, you can take the integral, and the area under the curve is the work done. Formally, we'd say work equals the negative integral of pressure d volume. And the reason it's negative is that typically we integrate from left to right as positive. If you're going from right to left, you would get a negative value, but the negative sign reverses that. So the negative here is all about direction. If you're going from left to right, the integral would be positive, but the negative sign makes the work negative. If you're integrating from right to left, the integral will give you a negative value, but the negative sign reverses that to make positive work. Any questions on that so far? So what if we took a different path? What if we went from initial, let's say we held the volume constant, or sorry, held the pressure constant, but increased the volume, and then held the pressure constant while we decrease, or held the volume constant while we decrease the pressure. We're still starting at the same initial values, ending at the same final value. We're just taking a different path, a different process to get there. How would that change the amount of work done as compared to the previous situation? Would you say that would be more work or less work or the same amount of work? Yeah, that's going to be more work because it's the area under the curve. And you could split this into two regions. The area under the top horizontal curve is this whole rectangle. The area under this vertical is 0 because you don't really have any area under a vertical line. So the area would be this entire, the work would be the area of this entire rectangle. And since it's a rectangle, you can just multiply the width, which is delta V, times the height, which is pressure. And it looks like that's more than that trapezoid we were looking at earlier. So this process involves a larger amount of work than the previous process, even though it was the same initial and final values, because most of the change is happening at a higher pressure. And the higher the pressure is, the more work it takes to change the volume. Any questions on that so far? Alternatively, what if we still needed to have this initial condition and this final condition, but we wanted to do only a little bit of work? Could we get the same initial and final? Could we set up a process that starts here and ends here, but involves a much smaller amount of work? What change could you make at the start? Yeah, if we decrease the pressure first, in fact, we could decrease the pressure by a very large amount. We could drop the pressure down to very, very low and expand the volume while we're at that very low pressure, and then raise the pressure back up to the desired final amount. In that case, the work done would be a very small quantity of work. So we'd only have this much area enclosed under the curve. That is a very small amount of work done. And of course, that's not always practical. There are limits to how much pressure difference the machinery can support. Because at 500 pascals, we're already significantly below atmospheric pressure. Atmospheric pressure is about 100,000 pascals. So if you're dropping the pressure extremely low, then your equipment has to be able to withstand the difference between the low pressure inside and the high atmospheric pressure outside. So the more different your pressure in the equipment is from atmospheric pressure, the sturdier your equipment needs to be. So large changes in pressure are not always practical. But that would be a way to make the amount of work very small, if that was the desired result. The overall idea I'm trying to get at here, though, is that the amount of work depends not on the initial and final conditions at all, but on the path taken. By taking a different path, like if we took, let's say, this path, we still have the same initial and final values, but because we're enclosing so much more area, we'd be doing a lot of work, or rather we'd be getting a lot of work out of it because this is work leaving the system. Any questions on work so far? Then let's focus on one path. Let's say we're looking at just the straight line path. If we're just talking about this straight line path, We could actually calculate the amount of work involved if we're talking about this shape, the area enclosed under the curve. What would be a good way to calculate the area of that region? Does that look like any shapes you already know an area formula for?
Looks like a trapezoid. So it's like 1/2 times height times base 1 plus base 2 or something.
Yeah, there are a couple of ways we could do this. One of them is we could treat this as a trapezoid. Trapezoid is going to have an area of base 1 plus base 2, essentially the average of base 2, the average of the two bases times the height. And the bases are the two parallel sides of different length. So in this case, this side and this side would be the bases. So we'd call this base 1 and base 2. And then the height is the distance between those. So this would be the height in this context. So this is one way you could do that. You could take the average of the bases, average of 500 and 100. And what is the average of 500 and 100? How do you calculate the average of a couple of values?
Sum of all the values divided by the number of values there are.
Yeah, and in this case, there's just two values, 500 and 100. So 500 plus 100 is 600. There are two of them. So yeah, we get 300 when we divide by 2. So the average of those two bases is 300 pascals. And then the height is just the difference between them. So from 2 cubic meters to 8 cubic meters, that would be 6 cubic meters. So 300 times 6 would be 1800. Pascals times meters cubed is joules. So the amount of work done during this process should be 1800 joules. Alternatively, instead of treating it as a trapezoid, we could certainly treat that as a triangle and a rectangle by splitting it up. So if we split this up into a triangle and a rectangle being this one, and then the triangle on top of that. How would we find the area of each one of those? For the rectangle, what would we do? Yeah, base times height. Base in this case would be 6 cubic meters. Yeah, times 100 pascals. And then for the triangle, half of 6 times 400. So that's going to be 600 plus 1200. So we still get 1800 joules. So two different approaches you can use here. Treat it as a trapezoid and use the formula average of those two walls times the distance between them, or split it up into rectangles and triangles. In fact, in general, no matter what the shape is, as long as the path is composed entirely of straight lines, no curves, you can always split up any shape made of straight lines into rectangles and triangles. So that's often the most effective way to do it if you don't have a formula for that overall shape. But if it's just a single straight line, you can always treat the area under it as a trapezoid. In either case, we get 1800 joules. However, since the gas is expanding, should we treat that as positive or negative? Yeah, we should treat this as negative. 1800 joules, because 1800 joules of work is leaving the system during this process. So that's the work done. No matter how you find the area, we now know that the work done during this process is negative 1800 joules. Any questions on that so far? Now let's say we wanted to find the heat. The problem is heat doesn't directly show up on this graph. But how are work and heat related to each other?
It's from the formula delta U plus Q plus W.
Yeah, we know that delta U equals work plus heat. And this is ultimately conservation of energy. We often call it as, we refer to it as the first law of thermodynamics. But that's really just a fancy way of saying conservation of energy. And that specifically is just the statement that the change in internal energy, which we usually call U here, is equal to heat plus work. That is, any change in the energy of the object has to come from the heat and or work applied to the object from elsewhere. And what do we mean by internal energy here? What types of energy are we keeping track of? Yeah, it includes thermal energy, bond energy, and also some others as well. Chemical energy, atomic energy, nuclear energy. Basically any energy contained inside the object. So we're not talking about mechanical energies. We're not talking about the kinetic energy of the object in motion. We are talking about the kinetic energy of the individual molecules vibrating or moving, because that's considered part of thermal energy, but not the kinetic energy of the whole object in motion, not spring potential energy of the object, not gravitational potential energy. We're not talking about any energies of the object in relation to something else, just the energies contained within the object, typically resulting from the behavior of the individual particles it's made of. So internal energy includes a lot of stuff. But if we're talking about change in internal energy, that's change in thermal energy plus change in bond energy plus change in chemical energy and so on. Of these, what's the only one that's actually changing that we care about here? For instance, in this process, yeah, we're assuming only thermal energy is changing. Chemical energy is, I mean, the substance could have chemical energy, but we're assuming there's no chemical reactions happening. So the chemical energy is not changing. The substance might have bond energy depending on what phase it's in, but we're assuming it's not changing phase. So there's no delta bond energy. And it has nuclear energy, but there's no nuclear fission or fusion going on. So that's not changing. The only thing changing here is thermal energy. So for our practical purposes, as long as there's no phase change going on and no chemical reactions, no nuclear fission or fusion, we can treat delta U as being delta E thermal, because that's the only part that's changing. And thanks to conservation of energy, we should assume that that change has to match any heat or work being transferred. Now, if we take a look at each piece of this individually, we know the work done based on the calculations we just did, the area under the curve. So we know that much. That's the area under the pressure volume graph. We can't directly tell heat from the graph, but we can calculate delta U. Since delta U involves a change, how do you typically calculate change? Delta anything really. Yeah, final minus initial. So if we know something about the final state and we know something about the initial state, we can use those pieces of information to calculate delta U. And note that for that, we don't even need to know what the process is. Even if we didn't know the process at all, if all we knew was the initial state and the final state, that's enough information to calculate delta U. Delta U is path independent. It doesn't matter what process you go through, what path you take. All that matters for delta something is initial and final values. So we can calculate delta U based on the initial and final values. And for that, usually using some formula, and since we're talking about E thermal, what formula do we already have for delta E thermal that might be useful here? Do we have any formulas for delta E thermal that we could use?
We use it was something like 1/2 times R times N times number of modes or something.
Yeah, the formula with number of modes is going to be really useful here. Using the general idea that thermal energy is N times R times delta temperature times number of modes over 2. Well, I guess if there was no delta, it would just be N times R times T. But assuming we attach a delta to both sides, we can assume that the number of moles is not changing because we're not adding or removing any more molecules. R is, of course, a universal constant. T is changing, and let's assume that the change in temperature is not significant enough to activate or freeze out modes. Let's assume number of modes is constant. If number of modes is changing, this is not necessarily valid, but let's assume that's constant. So what we could do here is if we know how many moles of gas there are, and we know the temperature initial and temperature final, or can calculate those, and we know the number of modes, we can calculate delta E thermal. Does temperature show up on this graph? Or what values do show up on this graph? What is this a graph of? Yeah, we can find it, right? We know pressure and volume at the beginning, pressure and volume at the end. So we could calculate the temperature initial and temperature final using the ideal gas law. So this is one way to do it. If you also know the number of moles, if you know how many moles of gas there are, you can back substitute and solve for temperature initial and temperature final. But an easier way to do that, instead of messing around with trying to calculate the initial and final temperatures, which you certainly could do if you need that for other reasons, but we can just make a substitution here. If we apply a delta to both sides, on the left side, it's possible that pressure and volume are both changing. So I'm going to leave P times V in the delta. That essentially means P final times V final minus P initial times V initial. The whole final thing minus the whole initial thing. But on the right side, what's the only part that's changing? Yeah, only the temperature. So since temperature is the only thing that's changing and R and N are constants, we can factor the N times R out of the delta. So we're left with just N times R times delta T. And that means we can make this substitution. Everywhere you see NR delta T, you can replace it with delta P times V. This is valid as long as you're talking about a gas. And that's exactly what we have here. This N times R times delta T can just be completely replaced with delta P times V. And then we still have number of modes over 2. And this is a great formula for thermal energy. This is a very useful formula because it involves pressure and volume, which we see directly on this graph. So we can calculate delta E thermal without even having to know anything about the temperature or how much of the gas there is. All we need to know is the initial pressure and volume and the final pressure and volume. And we also need to know the number of modes. So that's going to have to be either given or maybe you have enough other information that you can find it. For instance, if we knew delta E thermal and initial pressure volume and final pressure volume, we could solve for a number of modes. But let's say we know what type of gas this is. Let's say this is, assume this is a monoatomic gas. In that case, how many modes are there? Yeah, should be 3 modes per particle. So we can fill that in. Delta E thermal equals, and for pressure times volume, for delta pressure times volume, we're going to fill in final pressure times final volume minus initial pressure times initial volume times number of modes, which is 3 over 2. And if we fill those in, what's final pressure times volume? Yeah, pressure times volume, 8 cubic meters times 100 pascals, that's 800. And pascals times cubic meters is joules. We're going to look into what pressure is in more detail in 7b when we get into fluid flow. But for now, just keep in mind that the unit for the units pascals times cubic meters becomes joules. In fact, you could think of pascals as joules per cubic meter. It's usually written as newtons per square meter, but newtons per square meter and joules per cubic meter are the same thing because joules is newtons times meters. So we fill that in, 8 cubic meters times 100 pascals is 800 joules. And then initial pressure times volume, multiply the initial pressure times the initial volume, and what do you get? Yeah, 1000 joules. So that's the initial P times V value. So for the actual change in thermal energy, we can just take that difference in pressure times volume, final pressure times volume minus initial pressure times volume. Looks like that's negative 200 joules times 3 halves. So that'll be negative 300 joules. So that's delta E thermal. The change in thermal energy here is negative 300 joules, which also tells you from initial to final what overall has happened to the temperature.
Temperature must have dropped.
Yeah, the temperature has dropped because we know the thermal energy has decreased. You can also see this from the ideal gas law. According to the ideal gas law, temperature is directly proportional to P times V. So if you calculate P times V final, 800, and if you calculate P times V initial, 1000, overall the pressure times volume has decreased. Specifically, it's decreased to 4/5 of what it was. That means the temperature has also decreased to 4/5 of what it was. We don't know what the temperature is, but we know it has decreased to 4/5 of what it was, decreased by 20%. So we now know the change in thermal energy. And let's go ahead and fill those in. Now that we know these values, we know delta U is negative 300. And we also found work was negative 1800. So with that information, what else can we now calculate? What's the one missing piece left here? Yeah, the only unknown left is Q. So this is generally the way you can do this. Assuming you've got a fully labeled graph with all the information you need, you can calculate work by finding the area enclosed under the curve from the curve all the way down to the axis. You can calculate delta U based on initial and final values and whatever formulas are relevant, usually some variant of NR delta T times number of modes over 2, which can also be written as delta PV times number of modes over 2. So calculate delta U from the initial and final values, calculate work as area under the curve based on the process, and then heat is the only unknown left, so you can just solve for that. In this case, add 1800 joules to both sides, and we get heat has to be 1500, positive 1500 joules. So that tells us during this process, to make this happen, you have to add heat. You add 1500 joules of heat, you get 1,800 joules of work out of it, 1,800 joules of work leaving the system, maybe lifting up a piston, for instance. And also during this process, the gas gets colder, specifically losing 300 joules of thermal energy. Any questions on how all that works, how all these pieces fit together?
Can you ever determine Q directly, like we did for delta U and work?
Not on the pressure volume graph. The pressure volume graph does not directly tell you the value of Q. Later on, when we get to temperature entropy graphs, if you're graphing temperature on one axis and entropy on the other axis, I guess the other way around, temperature is the vertical, entropy is the horizontal. You can graph the same sorts of processes on a temperature versus entropy graph. And on that graph, the area under the curve is heat rather than work.
Gotcha.
But on the pressure volume graph, heat does not directly show up on the graph. The only way to find heat is by finding a change in energy and work, and then algebraically solving for heat.
Okay.
I guess the one exception would be if maybe the problem tells you how much heat is applied, because that's another possible variant. Maybe you don't have enough information to find work and change in energy, but the problem tells you how much heat was applied.
Oh, okay.
And then you can solve for something else. Like, for instance, in a case like this, maybe we have enough information to find work, but we don't know, let's say we don't know the number of modes. But if it tells us the heat, we could fill that in, solve for delta energy, set that equal to this formula, solve for number of modes, and then knowing the number of modes tells us something about what type of gas we're dealing with.
I see.
So that's another situation that might come up.
Okay, cool. Thank you.
One other thing to watch for, have you seen the term adiabatic yet?
Yes.
What does adiabatic mean?
Is it no work is done on the system?
Close. No heat specifically.
Oh, okay.
No heat transfer. So in an adiabatic situation, no heat is transferred to or from the system. And note that that does not mean that the temperature doesn't change. The temperature could change because even though there's no heat applied, what could be done to the system instead? What's the other way of transferring energy? Yeah, you could be applying work. So don't fall into the trap of thinking that adiabatic means no temperature change. Adiabatic means no energy is transferred as heat, but energy can be transferred as work. If there's no temperature change, we don't call that adiabatic, we call that isothermal. And isothermal doesn't mean no heat transfer. Isothermal just means heat and work balance each other out. So adiabatic means no heat transfer, but there could be temperature change because of the work. Isothermal means no temperature change. That just means heat and work cancel each other out. You've got the same, like maybe 500 joules of heat entering and 500 joules of work leaving at the same time. The situation where no work would be done, what would have to be true about the graph like this in order for there to be no work done?
But it has to be an isochoric graph where there's no volume change.
Exactly. Isochoric meaning no volume change. So that would just be a vertical line, which has no area under it. No work means isochoric. Volume is constant. Yeah, go ahead.
My question was, so work depends on the change in volume, particularly, or okay.
In fact, if you go back to the original definition of work from the study of motion, if you just got an object, doing work on it requires applying a force as the object moves some distance. In terms of the gas, we kind of replace we replace force and distance with pressure and change in volume. But the idea is if the volume's not changing, nothing's really moving. Like if you just got a rigid box where the walls cannot move, so the volume cannot expand or decrease. In that case, no work is being done. The gas is not doing any work on the walls because the walls aren't moving. The only way work can be done is if the walls are allowed to move, which would involve a change in volume. So no change in volume means nothing's really moving in a meaningful way, so no work is done. Any other questions on that one? All right, then let's take a quick look at that practice quiz because I wanted to make sure we get to that also. This one, I believe. Can you see this all right? Okay, so here we have a pressure volume graph, much like the one we were just working with. It tells us the initial and final volume or volumes at these two different states. And what's happening here? You got to be careful with this one because it shows a curve on the graph, but I don't think that curve represents the actual process. This curve is just, what does the text here tell us about the curve? Yeah, along this curve, temperature is constant. This curve is called an isotherm or an isothermal curve. An isothermal curve just means a curve representing all the points that are on a certain temperature. So yeah, any 2 points on this curve are at the same temperature. And it tells us what that temperature is, 292 Kelvin. So this basically just tells us that temperature A is 292 Kelvin and temperature B is also 292 Kelvin. So from A to B, there is no change in temperature. However, we're not going directly from A to B. It tells us we're doing this we're going from A to B in 2 stages. First, we compress the gas isobarically. So what would an isobaric compression look like?
The horizontal flat line.
I think that would be isochoric. Isobaric means what's not changing.
Pressure is not changing.
Yeah. So we got to keep the pressure the same, which means we're allowed to go up and down, but we're not, isobaric. Is I missing that? I'm sorry, you're right. It would be horizontal because we're assuming that the volume is changing, but we are, oh yeah, I think I was just looking at this backwards. We start with state B. So starting from state B, we are compressing the gas, so we're shrinking the volume, but keeping the pressure constant. So we start at state B, we compress the gas, changing the volume, until we get to the final volume we want. And in order to be able to refer to this, I'm going to put in a new data point here. Let's say we call this location point C, just so we have something to refer to. So we'll call this location C or state C. And then from C, we raise the pressure in an isochoric process. So in the next part, we're not changing the volume. We're just raising the pressure straight up. So we got 2 processes, B to C, keeping the pressure constant, and C to A while keeping the volume constant. And we know what those volumes are, 0.13 cubic meters, 0.16 cubic meters. And what else do we need to figure out here now that we have that much information?
We're missing pressure.
Yeah, we don't have any of the pressures, right? And we're going to need to know that in order to figure out how much work was done and the initial and final energies. So to find that, we know the volumes, we know the temperature. So what information could we use to bring all that together? What would relate the volumes and the temperatures? Yeah, we can always go back to the ideal gas law. And we want to know the pressure. So if we just isolate pressure here, that'll be N times R times T over volume. And I think we know it gives us the number of moles. We've got 2 moles. We know the temperature in both cases is 292 Kelvin. So we can just write this out twice, dividing by the two different volumes to get the two different pressures. So filling in some of these values, we know the N is 2 moles. We know R is 8.31 joules per Kelvin mole. And we know the temperature is 292 in both cases. So we just need to divide by the two different volumes. At A, looks like that volume is 0.13. At B, the volume provided is 0.16. So we can just do this calculation twice. We've got 2 times 8.31 times 292 divided by 0.13. And same thing with 0.16. And looks like we've got pressure A is about 37,331 pascals. And pressure B is about 30,331 pascals. So those will be the two pressures we care about. Any questions on that so far? And at that point, how would we find the work done during this process?
Area under the curve. We can probably split up into two different.
Yeah, because we're talking about the process from B to C. Area under that is just a rectangle. And also from C to A, that's isochoric. So how much area is, or how much work is done from C to A? Right, none at all, because there's no area under a vertical line. So we really just need the area under the B to C horizontal. That's a rectangle, so yeah, we can just multiply the difference in volume. And it looks like the difference in volume, yeah, the difference in volume is 0.03 cubic meters times the pressure at these two values, which is pressure B, so that's 30,331. So the work done is going to be pressure times change in volume, that's 30,331, times the change in volume, 0.03 cubic meters. And also, since we're decreasing the volume, that'll be a positive amount of work. So 30,331 times 0.03 is about 910. And I'll mark that as positive because work is entering the system. So that's the work done during that entire process. Because from B to C, we're adding 910 joules of work. From C to A, there's no further work done at all. And then for heat, again, we can't directly find heat from the graph. But how can we find heat, or what other equation ties work and heat together? What do work and heat have to add up to? Yeah, work and heat have to add up to change in internal energy, which, yes, in this case is thermal energy. And since we're talking about the whole process from B all the way to A, what do you know about the thermal energy at B and at A? What's the indicator for thermal energy? Yeah, the temperatures are the same, A and B, even though there's some changes in between. So this is not an isothermal process, but we start at 292 Kelvin and eventually we end at 292 Kelvin. And delta U only cares about initial and final values. So ignoring everything that happens in between, initial temperature and final temperature are the same. So delta U is 0. So if we fill in 0 there, what does that tell us about work and heat? Yeah, they're just going to be exact opposites of each other. So we know, yeah, right. We know that work is positive 910 joules, so heat has to be negative 910 joules, exactly. And that's generally going to be true for any process where the starting and ending temperatures are the same. Maybe a process that's isothermal, or a process that's not isothermal but starts and ends on the same isothermal curve, or any cyclic process. If you've got a multi-step process that eventually returns to the starting point, then you know the total work and total heat have to be exact opposites. So that's something very important to watch for. Anytime you know that the starting and ending temperatures are the same for whatever reason, then you know that work and heat overall have to be exact opposites. That doesn't necessarily tell you anything about the individual sub-steps, the individual sub-processes, but for the whole thing overall, work and heat have to add up to 0. Any other quick questions on that? All right, try out some more examples using this process. Find work as area under the curve, find change in energy from initial and final points and whatever formula is relevant, and then solve for heat as the last unknown. And remember, you can always use the ideal gas law as long as you're talking about a gas, and you can always use conservation of energy. Those are usually the two most useful tools there. So give that a try with some examples, and I will see you next time.